Okay. Thank you for the invitation to this nice conference. So today, I will talk about the emergence of biological-like functions in gel machines. I'm working with Tokyo Tech, and I'm basically working on the mechanical engineering. So this is my research purpose. So I'm interested in how we make autonomous gel machines just driven by chemical reaction networks. And the keywords are stimuli responsible gels and chemical reaction network. Okay, so this is the examples of stimuli-responsible gels. As you know, uh, stimuli-responsible gels change their volume in response to environmental changes. For instance, this is the thermal-responsible gels. When temperature is low, gel swells something like this. And when temperature is high, gel shows contractions, something like this. And basically, gel is very entropic materials, so we can control the shape or volume of the gels by changing the external environment. So this is the uh, chemical reaction networks. So I focused on the Berezov-Jabotinsky reactions, which is called busy reactions. Just you mix organic acid, oxidizing agent, metal catalyst, and strong acid. And then we can see the chemical oscillations. For instance, this is the chemical oscillations. Basically, the condition is stirred conditions. So you can see the periodical color changes of metal catalyst of, of this one. And this is the other aspect of these reactions. So you can see the chemical waves, something like this. This is kind of a reaction diffusion system. The situation is unsteered conditions, and you can see the something like this chemical patterns. So this is only just chemicals. So in the process of these reactions, there is so many chemical reactions actually, and this is a physical models of these reactions. So, okay, I don't explain the details. And basically, the process is very complex. And in the appropriate conditions, we can see the limit cycle oscillations, something like this. So previously, some researchers tried to design the oscillating polymer chains using busy reactions and also stimuli-responsive polymers. In the liquid systems of busy reactions, we can see the color changes of the redox reactions of metal catalyst, something like reduced state to oxidized state, oxidized states to reduced states. So this is limit cycle behavior in the liquid busy reactions. And when we make oscillating polymer, we can see the periodical solve and insoluble changes of polymer change, something like this is kind of a chemomechanical systems in micro scale. And when we apply, when we introduce the cross-linker to the polymer systems, so we can make gels. So, and we can make you know, large chemomechanical coupling systems. So I have developed the self-oscillating uh, gels at macroscopic scale. So we can achieve this kind of the volume oscillations of the gels. And also, of course, we can observe the peristaltic motions of the gels. So locally, swelling regions propagate inside the gels. And we can see something like peristaltic motions in the gels. Okay. So what I did before is I developed the locomotions of the gels driven by the busy reactions, like biological functions. And also this is the propagations of the torsions of the gels, something like this. And also we achieved large deformations of the gels periodically, something like this. So um, recently, our team developed artificial biological clock using this busy gels. Okay, so I will talk about the temperature compensations of biological clock in nature. So there is a mystery of the biological clock. So they shows the temperature compensations of, so which means that a property of the biological clock that does not fluctuate easily in response to the temperature, to the change in temperature. So look at the left side figures. Basically, the biological clock, they shows a constant period when we change the temperature. So this is a mystery in this area. And so my question is, can we create the temperature compensations using busy reactions? So, okay, there is a three conditions for the biological clock. First one is self-oscillations. Second one is response to light. And third one is temperature compensation. And basically busy gel, they show self-oscillations and also they respond to the light. So how we make a temperature compensations using busy reactions? So basically, the chemical reactions obeys Arrhenius law, as you know. So when we temperature is high, of course, frequency of busy reaction becomes higher. So in the solution systems, we cannot make a temperature compensations. So my idea is we use the interactive systems between busy reactions and gels. So basically, in the solution systems of the busy reactions, so the temperature affect the busy reactions. And temperature sensitive busy gel systems, temperature affect the busy reactions, and also they affect the gel. So there is some complex systems. So this is our idea. And the important things is when the temperature becomes higher, um, so volume fluctuations, which means that this is the concentrations of polymer, and the return metal catalyst is bonded to the polymer change. So the concentration is changed by temperature. And then, just a moment. Okay, sorry. So we modified the mathematical models of busy reactions. So we can introduce the effect of the polymer concentration to the mathematical models. And then we could evaluate the period using the busy gels, something like this. And from this theoretical analysis, we can predict that the temperature sensitive gel may show the temperature compensation, something like this graph. So in the experiment, we, just a moment. Okay, so in the experiment, we synthesized the such curves from the theoretical analysis, and then look at the right side figures. The y-axis shows the period, x-axis shows temperature. So we prepared two gels. One is temperature sensitive busy gels, and second one is non-temperature sensitive busy gels. Of course, non-temperature sensitive busy gel showed Arrhenius-like behavior, which means that when temperature is high, period becomes very uh, small, a little. And when about the temperature sensitive busy gel, they showed the almost constant period. So our model shows that volume changes offset the effect of temperature changes. So in my talk, I introduced biological-like functions of busy gels. We proposed the chemomechanical coupling systems using gels and busy reactions to create autonomous systems. And we showed interactions between chemical reaction and responsible gels. Thank you for your attention.
So thank you so much for your talk, Shingo. So maybe let me introduce for the next talk, but the next talk will be